In this video, we will investigate several more examples involving sketching parametric curves and eliminating the parameter. So once again, as a reminder, a parametric curve is an alternative method to representing a function that we typically could not represent via a single Cartesian equation, i.e. something that might not pass, say, the vertical line test. What we do for a parametric equation is we represent the x variable and the y variable individually as functions of t. We call t the parameter value and it lies in some interval, think something like a to b, so that for each value in that interval, maybe say a c value, there's a corresponding point on the curve. So here that corresponding point on the curve would be f of c, g of c. We plug in t equals c into those respective equations. So we're going to explore several more examples. Recall that to sketch parametric curves, one acceptable approach is to make a table of values and then use those table of values to kind of plot some points and then connect them in an intelligent fashion. So in this case, our parameter value t is anything bigger than or equal to 0. So technically we could have written here t is less than infinity. And let's just go ahead and start off by looking at a few values. When we plug in t equals 0, we get x is 0, y is 1. When t is 1, we find that x is 1 and y is 0. When t is 2, we have x is the square root of 2 and y is minus 1. When t is 3, x is the square root of 3, y is minus 2. And when t is 4, x is 2 and y is minus 3. And note, all we are doing is just plugging those respective t values into the given parametric equations. So let's get a few points plotted. So we have 0, 1, and this would be when t is equal to 0. We have 1, 0, square root 2 minus 1, square root 3 minus 2, and 2 minus 3. And this roughly gives us an idea of what this curve is going to look like. Connecting the points, something that looks like this, where the final point that we've plotted corresponds to t equals 4. So maybe just a bit cleaner of an image, but we should see the correspondence to our previous slide. Let's once again go ahead and eliminate the parameter. That is, rewrite these as a single equation that does not involve the parameter t. And here the observation to get us started is that we can write t solely in terms of x. So having this x equals the square root of t, we can write t is equal to x squared. And going up to the equation for y, we can simply replace that single t with x squared. So y is equal to 1 minus x squared. Now, a careful observation that we have to make is when we have written down x equals the square root of t, the assumption here is that since t is bigger than or equal to 0, or x is equal to a square root, we know that x is bigger than or equal to 0. So for this final equation that we've come up with, there is a domain that goes with it. It's the portion of the curve y equals 1 minus x squared with x bigger than or equal to 0. So let's investigate one last example of sketching some given parametric curves. And we're going to change it up a bit here and look at some trigonometric functions. We're going to let x be 5 cosine, y 4 sine, and the parameter value bring us through a period of these trig functions, 0 to 2 pi. So some nice values to work with in terms of trig functions would be 0, pi over 2 pi, 3 pi over 2, 2 pi. And we could certainly go into more detail if we need to. We could go to pi over 4, 3 pi over 4, etc. But let's use this as a starting point and see what we come up with. When t is equal to 0, we get 5, 0. And once again, we're just plugging that t value in to the given equations. Cosine of 0 is 1, sine of 0 is 0. When you plug in pi over 2, we would have 0 for x, 4 for y. When we plug in pi, we would have minus 5 for x, 0 for y. At 3 pi over 2, we would have 0 for x, minus 4 for y, and then at 2 pi, 5 and 0. So plotting these points for t equals 0, we have 5 comma 0. And I put a little comma there because we've seen here already that we have that same point again at 2 pi. So I'll just go ahead and indicate that now. At pi over 2, we have 0 comma 4. And this would correspond to t equals pi over 2. At t equals pi, we have the point minus 5 comma 0. At 3 pi over 2 for t, we have 0 comma minus 4. And I'm going to just go ahead and connect these as follows. And we're going around here in the counterclockwise direction. And the observation to make is that this appears to look like an ellipse. And if we check the points at, say, t equals pi over 4 and t equals 3 pi over 4, hopefully this would confirm what we're finding. But let's go ahead and eliminate the parameter and just verify this analytically. So I'm going to make an observation here and kind of a reminder for you. So something we've seen many times in the past is that if you have cosine squared of t plus sine squared of t, that will be equal to 1. It's one of the Pythagorean identities. So what I'm going to do is try to kind of modify the equations we have. If I want to get a cosine out of this x, I need to divide by 5. So I'm going to think of this as being 5 cosine t over 5. That's just a fancy way of writing cosine. And then I'm going to square it, so it's really just cosine squared. And looking at the sine, from the y, if we divide by 4, we would just have a sine of t. So let's say plus 4 sine t over 4. So if we write it this way, it's cosine squared plus sine squared, which we know is 1. So that's really x over 5 squared plus y over 4 squared equals 1. Or let's write this as x squared over 25 plus y squared over 16 equals 1. And this would be the Cartesian, or maybe think implicit representation of this curve. And note this matches up exactly with our picture because the x squared over 25 is telling you that the points plus or minus 5 comma 0 lie on the curve. And from that y squared over 16, we're getting that 0 plus or minus 4 lie on the curve, which are exactly the points we found in our previous table. Now I'd also like to observe that there is something much more general going on. And some common parametric equations we might see would be x equals r cosine of t, y equals r sine t, with 0 less than or equal to t less than or equal to 2 pi. So in this case, the associated parametric or Cartesian equation would be x squared plus y squared equals r squared. That is a circle of radius r centered at the origin. Similarly, if we have x is equal to a cosine t and y is equal to b sine t with 0 less than or equal to t less than or equal to 2 pi, following the steps that we've already done to the left, this will end up being as a Cartesian or implicit curve, x squared over a squared plus y squared over b squared equals 1. So it would represent the equation of an ellipse. Another common question you might wonder is, what if we didn't have all of the 0 to 2 pi? Maybe just 0 to pi. Well, in that case, 0 to pi, you would just do the top half of the ellipse, and that's why it's careful to think about plotting in terms of points as well, so that you can see maybe what the starting point or initial point of the curve is, and where it finishes, that terminal point for the curve.